Up until now, all of our data analysis discussions have kind of begun with observations. So like rows of the X matrix or the data matrix, or there's other names. Um, a lot of times this is not where you begin, but instead you begin with a collection of some sort of measure of similarities between two different observations, or differences or distances between observations. And in this lecture, we're going to go over a bunch of different ways to compute those differences or similarities, or distances or similarities. Now, there are lots of different ways to do it, essentially an infinite amount of ways, but we're going to try to sort of group those into different kind of, or sort of categorize them based on the rules that you use for doing the calculation. It often is the case, actually, that the differences that you start out with in some sort of analysis aren't even computed from one of these sets of rules, but instead they're just inherently differences or distances or similarities. And you use your understanding of how one can compute distances and similarities to try to understand maybe something about the observations that could go along with the distances or similarities that you've got. We'll talk more about that in the lecture after this one, but for now, let's just focus on what are the different ways to compute distances and similarities. All right, let's get started. So today we're going to talk about, we're going to introduce two new concepts, distances and similarities. And really the whole purpose of this chapter is just to kind of get you comfortable with what they are, and with understanding kind of like how they might be used and their various different properties about how they're defined and so on. So normally, so far, when we talk about analyzing data, we've always started with this sort of matrix of observations, but that is not always how you start. So often you don't start with that matrix. And what for us, it's been an n by p matrix X. And you also don't start with that matrix or with its rows, which we've been writing as, I think when I've been on top of things, as lowercase x with a subscript I. So that's row I of the matrix X as a vector, written as a column vector. So I is equal to 1 to n different rows of these guys. And each of those has p elements in it. You often don't start with either one of those things, but instead you start with the distances between them. And sometimes that's all you actually know. So let me kind of draw a picture here of what I mean by this. So I'm going to draw a picture in like p-dimensional space, right? So let's draw 4 different observations. So there's 1. And so we'll name these guys. And so this is meant to be in some p-dimensional space, right? So it's sort of an abstract drawing. So drawn in p-dimensional space. That could be like a 10-dimensional space or something abstract like that. And so if you have these 4 observations, then there's a bunch of different distances that you could define, right? So there's the distance between observation 1 and observation 2, and we'll call that guy D12. I think in the notes you'll see lowercase d, but that's fine. Then there's this distance here between 2 and 3, D23, and then all the other ones I'll draw on here. Oops, that one didn't make a straight line. Can't get that one straight for some reason. That's D14. And then the diagonal ones. So this goes between 2 and 4. Where can I fit that? D24. And then just sort of make it look like it went underneath it there. And this is D13. right? So you have a bunch of more distances here than you have points. So those distances are often kind of the starting point for your observations. Sometimes you really don't even have the observations, but you only have a notion of these distances. So instead of using x as your starting point, you study these distances. And I'm calling them distances here, but they could also be what we call similarities, which is some kind of measure about how similar the two different, any of the two pairs of observations is. And we'll get to that at the later part of the lecture. So we'll call these distances between observations. Right, and so collectively they'll make some matrix D, and it looks like this, right? So it's the collection of all the Dij. And the size of it, the dimensions are, right, so if there's n different observations, then this is n by n matrix, right? And again, I'll just say, in your notes, I think these are lowercase dij. I don't find it so important to use lowercase letters for the elements of a matrix, but I also kind of especially don't like using lowercase d because it makes me think of derivatives in calculus, and so I'd like to reserve it for that. Okay, and so there are a lot of these distances, right? More than the number of points, and we can count them up, right? So how many are there? So the number of unique and let's say non-zero distances. And so the unique part is there because that distance matrix may be symmetric. And the non-zero is there because the diagonal elements may be zero. But we'll get to some nuances about that in a second. So this number, if you count them up, right, if you think about a square matrix, it's n by n. And you only want to count half of the off-diagonal elements. So the total number of elements is n squared. You subtract off the diagonal, and then you only want half of those. And so you can rewrite that as 1/2 n times n minus 1. And so that's the number of distances that you could record for such a set of observations. So you can, for our case, 4, what is that? So that's 4 times 3, so that's 6 different distances. And that's what we have there. And so this seems to work. But now this formula is only true if, so this is a crucial point, it's only true if two conditions are satisfied. Dij is defined in such a way that it's always equal to dji. So in other words, the matrix of distances is symmetric. And this is also required that the diagonal elements are 0. Now those two things might seem super intuitively clear to you, that that's how distance works. When you measure the distance between two things, it doesn't depend, the result doesn't depend on which thing is first and which thing is second. And the distance between one place and another and itself is 0. But you don't have to get too exotic before you can find situations where that isn't true. And so I'll just say there are many different definitions of distance, and they don't all obey these properties. So the simplest example, I think, where you don't have to do anything fancy and you can understand that these distances, like, let's say, aren't symmetric, would be, let's say that distance wasn't actually a length of space, but was a length of time, and it represented the time it took to drive between two locations. And there's real-life traffic present. And so clearly, the distance from point A to point B, which then it really means the travel time between point A and point B, might not be the same as the travel time from point B to point A, because the traffic might be different, getting from one to the other. That one doesn't so easily explain the diagonal elements being non-zero, unless you have some idea of some path that you had to take that would make non-zero travel times to start at one place and finish at the same place. But so there's lots of these different definitions, and often it's not necessarily super clear what are the best, what is the most appropriate definition of distance for your particular problem. But let's just introduce two super common definitions. So these are two different examples. So example number one, let's highlight that as an example. This is going to be called Euclidean Distance. And this one is probably the most intuitive and familiar to you. And I'm going to underline it in orange because it's going to appear in orange on the drawing. It also has another name. It goes by the name of the L2 norm. And I guess we can put that in orange as well. L2 norm. Make that too clear. And this one is pretty, it's the one you kind of learn as a child. That it's also in the notes. I think it's called the Pythagorean distance because you find it using the Pythagorean formula. So looks like this. So the square of the distance between I and j, observation I and observation j, looks like this. So first I'll write it as a sum, but I find that kind of awkward. So it's a sum over some index that we'll call k, equaling 1 to p of x row I column k minus x row j column k, so the difference between the two things, squared. And you can rewrite this, I think, in a simpler way, like this. So it's the vector difference between xi and j dotted with itself. I also like this version of writing it because you can see it. I think you can see more clearly some of the geometric properties of this distance. So for example, if you multiply that dot product through, what you get is the squared magnitude of xi plus the squared magnitude of xj, and then minus this sort of cross term thing, twice xi dotted with xj. Right? And if you remember your geometric picture of vectors and what the dot products mean, you can write this out, or you can draw a picture for these two things. So for the two vectors and the distance between them. So let's say that's xi, and then we'll say this is xj. Oops. And they're meant to come together here. And then let me actually phrase it like this. So let's not say that, that is the vector xj and the vector xi, but let's just label their magnitudes here because that's what shows up in our our formula for the distance. And the Euclidean distance here is this distance here. Right, and so that's dij. And from the geometric picture, you can see this kind of famous result. Like if we make this angle between the two vectors I and j theta, if we call it that, then this formula here is called, so it still looks like xi squared, the length of the vector I, xi squared, length of xj squared, minus twice the length of xi, length of xj, times the cosine of that angle between them. And this thing has a name. This is called the Law of Cosines, which you might have used before in math or physics classes or something like that. But it's super easy to come up with. It just comes from taking the difference of these two vectors and squaring it, and that gives you the law of cosines. It's not important that you know that name, but it's just, I think it's a helpful geometric picture to see kind of what this L2 norm is, or Euclidean distance. And of course, it's called L2 because of the 2 here in the exponent there. Okay, so let's look at one more quite common distance that we'll encounter, but there are lots of other ones. So another example here. And this one is called the Manhattan distance. Which is a reference to the city of Manhattan, New York City. And I'll underline this one in red because I'm going to draw an example of it where the Manhattan distance is in red. And it's also sometimes called the L1 norm. Put that in red again, too. And this one, the formula for it is straightforward. The geometric picture is also pretty straightforward, I think. So for this one, the distance between these two observations is defined like this. So it's a sum over all of the variates or features. Sorry, that should be a sum over k. K equals 1 to p. So there's p different columns of the absolute value of the difference between the variates for the two different rows. So x ik minus x jk. Right? And so this is called the L1 norm, I guess, because if you want to think of an exponent there of that difference, it's 1. And I'll draw a picture of it, what it looks like in 2 dimensions. So in 2 dimensions, this is what it looks like, and it's the reason for its name. So let's say that this point over here, let's draw here, is x1. And I don't know, let's say over here is x2. And what I mean by that is those points are like where the tips of the arrows go as they start from some origin and land at those points. And so if I'm using x and y axes that look like this, right, for the different columns, right? So this is like variant 1 and variant 2. Then the absolute value for the difference between these two guys along variant 1 looks like this. Right, that's the distance between them along the variant 1 axis. And the absolute value of the distance between them along the other axis looks like that. And so that complete red line, this is called the Manhattan distance. And you add up those two different lengths. And the name for this comes from, again, it's a reference to New York City, where the streets are laid out, not entirely, but for the most part on a relatively regular grid. In fact, so these things that go this way are called streets, and the things that go north-south are called avenues. And so sometimes it's called the taxi distance or something like that. And you can see where the Euclidean distance would be on here. It's different. Right? Here's where the Euclidean distance would be. Just like that. And so, yeah, so that's the Manhattan distance, or the taxi distance, and so on. Both of these are commonly used in different circumstances. I think there's some examples given in the notes for where you might encounter these. But yeah, they're both relatively common. But often something else, some other thing, is better. So both are common. Both these guys are common, but often something else is better. So that example of the travel time between two different places is not among these things. And so let's just make a list of sort of what kind of properties you want. So in your distance measure, so ideal properties. And there might be a lot of different properties that you might want, but I just want to kind of outline some really simple aspects that you might want, some sort of, I don't know, kind of vague or minimal requests, sort of. So what you want is, first of all, you want the distance measure to be easy to understand. So that you can have some intuition about it, or intuitive. Intuitive. Hope that's how you spell it. Who could say? And you also want the distance measure to really not have overly strong influence on your analysis. So you want does not overly influence, or conclusions rather. Maybe it's a better way to say that. Okay, but those are just some sort of vague, like, ideal properties, and but here are a few kind of named properties that are more specific for distance measures. Okay, so the first is going to be, so some of these have names that you would kind of expect. Some of them have funny names. This first one, I don't know why it's called what it is, but it's a funny name. So this one, property number 1, is that XA equaling XB happens if and only if, which you write like this. So I don't know if you're familiar with this as if and only if DAB is 0. That is to say, if DAB is 0, then it must be the case that XA is equal to XB, and conversely, if XA is equal to XB, it must be the case that DAB is equal to 0. And this one we give a sort of funny name, I think. In the notes we call this identity of indiscernibles. That's the name for that property. And property 2, this one is a simpler name. So this one says that XA, if XA and XB are not equal to each other, this happens if and only if the distance between them is positive. And this goes by the name of non-negativity. Right? A third property. So all these, I think, so far seem like super obvious. Like, why would anybody write these things down? But you have to think of some more creative ideas about distance, like that travel time thing. And then you see why it's important to kind of distinguish different types of distances, maybe. So another one is that DAB is always equal to DBA. This is named. And this is just called symmetric. And the last one is a little more complicated. This one says that if you have 3 different distances, so let me draw them first. Or sorry, 3 different observations. Like this. And I'm trying to make that triangle not look like a right triangle. So let's say this is A, B, and C. So those are 3. Oh wait, that's not what I have in my notes. I'll make a mistake. So I got B over here and C there. So this guy is distance DAC. This guy is distance DAB. And this one, of course, is then DCB. And this property that I'm about to write down refers to the relationship between those three different lengths, and it says that the distance AC, right, so this one here, it says that it's smaller than or equal to the sum of these two guys. And I think you can see that there. Like, these two guys are going to be, at shortest, they're going to be the same length as DAC. But most other situations, in all other situations, they would be longer. And so we write this as less than or equal to DAB plus DBC. And this thing has a name called the triangle inequality. And you could see it kind of in the Law of Cosines thing here as well, sort of. So this is the squared distance here, and this is the squared, the sum of the squared distances of these two lines here. And then you subtract off something. I don't know, you can kind of see it in this thing. Okay, now I just want to say, this is sort of a fun, I think, kind of a fun fact, an interesting thing. So fun fact about nature. I don't think this is in the notes, but the nearest thing to what we call distances in nature are not really so much lengths in the usual sense. It turns out that those are kind of observer dependent. That was a discovery made in the early 1900s by Albert Einstein, or rather it was an idea he suggested and then people verified it. So nature's sort of best distance, distance is not really so much lengths, but we say it's distance between space-time events. So that's a sort of a funny name, between space-time events, and let's name them. So a space-time event is a place and a time. So let's say this is at time, this is event A is at time, has time A, and then it has like 3 spatial coordinates, XA. So that's event A. And event B has a time associated with it, and it's at some particular location. So the classic example of a event is like a firecracker going off. It happens at a particular time and at a particular place. Then, so it turns out that nature's way of having a uniform or universal definition of some kind of distance between these kinds of events, it turns out that it violates all of those properties except property 3. So all 4 of those properties, with the exception of 3, so it is symmetric. But if 2 events are the same, it is not the case that 2 events have to be the same if their space-time interval is 0, the interval between them. And it's also not the case that the distance between 2 space-time events is always positive. It can be negative. Symmetric does happen. The triangle inequality does not necessarily hold. And the way you write out space-time distance, in case you're curious, so an example in empty space. It turns out this gets influenced by gravity. So in empty space, DAB, between these two guys, squared, it looks like this. It's minus a constant c squared times the time difference squared, and then plus the usual Euclidean distance between A and B, like that. Now, I only bring this to your attention. So, and c, this constant c, if in case you're curious, is the speed at which light travels in a vacuum. I only bring this up because I think it's sort of interesting. We are going to run into cases where you're making distances between things that aren't, like, not all of the columns are going to be of the same type. So sometimes they were in a lot of the things we did. Like in the Pima Indian data, for example, all of the columns were something called genetic expression. They were all the same kind of thing. But it was not always the case, right? So for like the car data, one column might represent horsepower and the other column might represent number of cylinders or something like that. So you're smushing together different columns of totally different physical properties. And as a result, you get the right way to define distance might be kind of complicated. Okay, so I'm going to introduce some terminology here that's a little bit statistics specific. So this is for stats people. So some terminology here. We say that a distance is a metric distance if all four of those properties above hold. So 1 to 4 hold. So these properties that we saw, that we laid down up here, the named properties. We say it's semi-metric if only properties 1 to 3 hold. So property 4 is violated. And we say it's non-metric non-metric distance. This is what we say it is if any of properties 1 through 3 is violated. If any of 1 to 3 gets violated. So again, this is a pretty statistics specific terminology, but nevertheless, we saw our two examples, right? We saw the Euclidean distance, and we talked about the travel time distance, but so we saw Euclidean distance. And let's go back and look at these properties. Does Euclidean distance obey any or all of these properties? So you got to sort of stare at them for a while. So certainly 1 and 2, definitely, and 3, and 4. You can sort of see it must be true because we are drawing it on a flat surface and talking where we normally use Euclidean geometry. So this guy obeys all 4, and it's called a metric distance. And the other one I wanted to mention is the travel time. Which we never really wrote down a formula for. But again, what I mean by this is travel time between physical places on roads where there's traffic. This one is non-metric. Right, both 3 and 4 up here are violated, so it's not symmetric, and the triangle inequality doesn't necessarily hold. Yeah. Okay, so now we'll introduce similarity. So similarity is often used kind of as an alternative to distance, like, so similarity. And really, it's sort of, distance tells you how different two different events are, or two different observations are. And similarity sort of does the opposite. It tells you how similar the two different events are. And it's some kind of quantitative measure. And there's just like with distance, there are lots of different definitions you can use. So this is often used in place of distance. So sometimes you get a collection of data, and what you're given is just a collection of distances or something like that between observations. Other times you might actually just be given a measure of how similar different observations are in some matrix form. So this is often used instead of distance, or in place instead of distance. And I'll just give like an example. I'll just start off with a simple example so you can kind of see how does this actually work. So this is just one example. I think this actually is used in the book for ID 5059, but I can't remember. I think that's where I got this. But this thing is Sij. So the similarities are stored in a matrix that we would normally call S. And it's defined like this. So it's an exponential, so e to the minus gamma, where gamma is some positive constant, and then the distance squared, xi minus xj squared. So gamma again is greater than 0 and constant. So this guy, if you think about this, does it make sense to call this a similarity? So suppose xi and xj were exactly the same observation, then their difference would be 0. And so we'd have e to the minus 0, which would be 1. And suppose their difference was not 0, it's like some number like 5. Then that difference squared would be 25, and we'd have e to the minus 25 gamma. And so that's smaller than 1. It's 1 over e to the 25 gamma, right? And so this gets smaller for things that are dissimilar, and it's large, or it's 1 actually, for things that are the same. So sometimes you're given this and there's some obvious way to connect it to distance. So sometimes you use... So sometimes if you start out with similarities, you introduce complement distance. Defined by the Sij. So if you maybe started with a matrix of similarities, you can define distances, and some common examples of that definition are to do the following. You say, okay, well, Dij is going to be 1 minus Sij. That's a common way to define distance in terms of similarities. Or another one is Dij is the square root of 1 minus Sij. But you don't have to do this. And in fact, if you look at that example above, that S is clearly related to the Euclidean distance. It's Sij is equal to e to the minus gamma Euclidean distance squared. So which is neither of these. So neither of these two relations I wrote down converts you between distance and, or at least Euclidean distance, and Sij. But these are common measures. And it's usually, again, given when you actually don't have some inherent measure of distance. All you have are the similarities, and you want to construct distances. Okay, we're going to have 2 more topics left today. I want to talk about a units issue, which might kind of surprise you. You probably won't be surprised to hear me talking about units, but it has there's a surprising problem. Units issue. And we'll see this by an example. And then in the end, we'll introduce binary. How do you compute similarities for binary variables? That'll be the last thing we do in this lecture. Okay, so let's try out Euclidean distances on a particular data set. So try Euclidean distances on the following data set. So we'll say x is equal to 10, 50. That's the first row. Next observation is 15 and 100. And again, you don't always have this x. It's not always something you know, or maybe it doesn't even exist. 20 and 75. And let's suppose that these things are, this is a length in centimeters. And this guy is a weight or a mass in grams, right? So that's what those two different variates are, those two different columns, a length in centimeters and a mass in grams. And then if you go ahead and compute the Euclidean distance, what you would get, and you can try this, is the following. So you get zeros on the diagonal, right? Euclidean distance is, I forgot the name of that property already, but but so this element here is 50.2. So that's the distance between, which one is that? So that's row 1, column 2. So it's the distance between this point and this point in two-dimensional space, right? So you should be able to verify that. And you could just do it by hand. You don't need to like break out R or anything. And then the distance between 1 and 3 is 26.9. And the distance between 2 and 3 is 25.5. And you can verify all these, right? And then those values are the same down here as up on the top off diagonal, right? Okay, now change the units. All right, and so we'll change lengths to millimeters. All right, and we'll see if that makes a difference, right? So there's 10 millimeters in a centimeter, and it makes a surprising difference, all right? So I'll just show you the result. You can do the calculation yourself, but so here's what you get for the distance matrix. 0 and then 70.7. It's probably not a surprise to you that it changes this matrix, but hang on for a second. And this one is 55.9. And then 0 down here again. And again, these are the same. So what I want to highlight here is, look, where are the biggest distances here? So in the first matrix, it's here, right? And in the second matrix, it's also here, right? And so this is going to be the largest distance. Or most different, or something like that. And then where are the smallest distances? Right, so in here, the top matrix, it's here. But on the bottom matrix, it's this top right corner. So what's odd here is that, so the green is like the nearest pair of points. So this seems odd. Like the change in units didn't just change the values of the distance matrix. It actually like reordered the nearness of the different observations. So depending on which of the units you use, you might say that observation 1 and 3 are the closest together. Or you might say that observations 2 and 3 are the closest together. And so I think you should be able to see from this that this is sort of a problem. And the reason this problem, so the cause is that we have an issue with our units, which is that we made up a unit which doesn't really make any sense. Right? If we used Euclidean distance, it would be the first column, so that's like centimeters squared, plus, and for the first version of the matrix, grams squared. And if you think about what this is not the kind of unit you ever encounter in natural calculations. Like, this is not a real, like, this is some kind of non-physical sort of meaningless unit, or you might just call it a strange unit. Right, it sort of gives you nonsense. So yeah, so this is a thing to be aware of when you just start announcing to yourself, like, well, of course we'll be using Euclidean distance. What else is there? You can create all sorts of troubles. Like it's really more troubles than you might have guessed, I think. Okay, so we'll finish off here talking about similarities for binary variables. And binary variables are just things that are either like factors, like they're categorical things that have only one value or another. They could also just literally be a value of 1 or a value of 0. But so let's just make an example. So we'll say, consider these two different binary variables. They don't have to be two of them, but I'm using two. I'm going to work in pairs. We'll say L is equal to, it's a property for some real estate. This is from ID 5059 if you're taking that module, but you don't have to know that module. Let's say you're describing real estate, and this is L stands for whether or not the property is in London. So this is like London or not London. Oops, if I could spell. Right? And so you could give numbers to these. You just call this 1, and you call this guy 0. And so that's a binary variable. And then you could have another one, T. So this is from some UK property analysis. And this one is going to be also binary, and it's going to be either the property is a semi-detached, which in American English means like duplex, which has a different meaning here, or not semi-detached. And the short name for that is semi-D. And again, this is either 1 or 0. You could use other numbers, of course, but this is the numbers I'm choosing here. And then let's say you make a little table. So you can make what's called a two-way table. A two-way table. And the table looks like this. So down one axis is the value of t. So this is t equals 1 and t equals 0. And then along the columns, or I always forget how you read this, but the labels of the columns are L equals 1 and L equals 0. And then you count up all the properties. So how many properties have both L equals 1 and t equals 1? And you say, okay, well, that's a number, and I call that number A. How many properties have L equals 0 and t equals 1? That's something else, and I call that B, and so on. And so you name these things. So this table is called a two-way table. And so here, so again, just A is equal to number of observations with t equals L equals 1. Right, so that's how this is defined, and the other ones are defined similarly. You can use this table, those elements A, B, C, and D, to create different similarity measures for these binary variables. And I'll just tell you the names of two of them. I think some properties of them are discussed in the notes, but I'm just going to give you their names. So some binary similarities. So some definitions of similarities for binary variables like this. So one is pretty obvious. When you look at it, you can understand what it is. So it looks like this. It's A plus D divided by A plus B plus C plus D. And so what this is A and D are the two, it's counting up all of the observations that had both t and l equal to each other. And the denominator here is just all the observations. And so this is the probability that L is equal to T. So sometimes this is used as a similarity measure. And this has a name. It's called an association coefficient. I think it might also usually be associated. The name of the people who invented this might be on here. It's in the notes at least. Sokol. And another name, Michener. I'm not sure how to say that. I don't know where the name is from. The name's not super important for us though, right? It's clear what this is. So this is the probability that the two variables are the same. And then there's another one that I'll introduce, which has an intuitive definition too, but it's not as easy to see, I think. But I'll let you look at it. So it's A divided by A plus B plus C. And I'll just tell you the name of this. So these three lines mean defined as. This one is called Jacquard's coefficient. I don't know who Jacquard is. I'm ashamed of myself. I should look it up. And this one also has a probabilistic interpretation, but I will leave it to you to look that up in the notes. I really just wanted to show you a different example. This is also used as a measure of similarity. So these are just two ways to measure similarity for pairs of binary variables. Okay, so I hope you now have a better idea of how do you compute distances and similarities if you've got a collection of observations. In the next lecture, we're going to start to discuss some data analysis methods that use these distances and similarities. But we're going to actually see that you don't actually have to have computed the distances or similarities. Sometimes you're just given them by themselves, and they were maybe never even computed from anything at all. So the kind of standard or classic example of that is if you gave a survey to a bunch of people and asked them to compare things. They said like, oh, this movie, how similar was it to this other movie? And they just give you a number. You don't know how they did that calculation. Maybe they don't know how it is just some sort of opinion. So you can certainly run into situations where you have distances and similarities for which you didn't actually have any inherent observations that those were calculated from. And you need to be able to, or it's useful to be able to kind of go back and forth between the two, or at least to sort of imagine going back and forth between the two. The distance information or the observation information, or the similarities in the observations. But anyways, that's for next time. I'll see you then.